Okay, and then on to the last section, which is continuity and asymptotes. So most of the time, when we have a function f of x, if I take the limit of that function as x goes to a, then that's going to be equal to f of a. And in fact, sometimes it's hard to imagine why that would not be true. I'll show you one picture in a second. But if you think about the quiz question you just did, that is actually well defined. There's a very good choice of a number to choose for that when x is equal to 1, but the function's not defined at 1. And so this is kind of the idea of continuity. If this blue curve is my function f of x, then you can think of it as a function's continuous if I could draw the curve associated with that function without lifting my pencil off the piece of paper. And so if I have a point A on the x-axis and input A, and if I just move along the curve until I get to A, then the value of that point should be equal to f of A. And so that's actually the concept of continuity. That's the definition of continuity. So we say a function f is continuous at a point A if the limit as x goes to A of my function f of x is equal to f of A. And then we can be a little bit more precise about this. So we say a function is right continuous if, as I look at points that are greater than A and kind of move down towards A, the limit of f of x is equal to f of A. And then we have the same idea. A function is left continuous at A if I look at points less than A and move towards A, the limit as f of x goes up to A is equal to f of A. And so clearly, if a function is continuous, it's going to be both right continuous and left continuous. And then we'll also say a function is continuous on an interval. So I named my interval CD, so that's just the lower limit C up to an upper limit D, if it is continuous at every point A in that interval. And so this is kind of an idea of what a discontinuity would look like. So if there is a jump in the function for one reason or another. So this is pretty much the same thing I had on the last slide. It's just at this point A, I decided to add a little bit to f of x. So that explains this jump here. And then the open circle means that I follow this curve up to every point that's less than A, but not A itself. And then this solid circle means that I start at A and for every point greater than A. So if the solid circle were down here, the open circle would have to be up here because the function can only be defined to be one value at any given input. And it's just going to affect the definition of whether it's left or right continuous at that point. So here, is f of x continuous at A? And I would say no, because if I look at the limit as I go towards A over here, if I was bouncing back and forth, sometimes I'm going to be quite a bit less than the function value. And no matter how thin I make my interval, I'm always going to be able to, if I choose an epsilon that makes a range around this solid dot, say halfway in between the open circle and the filled-in circle, I'm never going to be able to get any points on this side into that range. So it's definitely the limit as I approach A from the left-hand side is going to be less than the value of the function there. So it's not continuous. Is it right continuous? So if I forget about this lower curve and only look at the stuff on the right-hand curve, as I move down, since I've defined my function to be the value of the top curve at A, it is going to be right continuous. But the reason that it's not continuous is that it's not left continuous. So as I approach this point A from the left, the limit is this open circle, but the value of the function is the filled-in circle. So that's the sort of the way we want to give a rigorous definition to this idea of of continuity. And so then, again, in a first-year calculus textbook, you're going to be able to find lots of theorems about when is a function continuous. And so I'm just going to list off a lot of these very quickly. So let f and g be continuous functions. So they're continuous at a point A. And again, c is just going to be a real valued constant. So the sum of two continuous functions is continuous. The difference of two continuous functions is continuous. If I multiply a continuous function by a real value, that's also going to give me a continuous function. If I take the product of two continuous functions, that's going to be a continuous function. And as long as the denominator is not equal to 0 at the point A, then the ratio of two continuous functions is also going to be continuous. And again, this is a pointwise definition. So this is only continuous at a point A. So all of these have to hold on an entire interval for these functions to be continuous on that interval. Any polynomial, so one useful interval is R. That's all of the real numbers. So everything greater than negative infinity and everything less than positive infinity. So any polynomial is continuous on the real numbers. And then the following functions are continuous on their domain. So the domain is just where the function is defined. So sometimes you have to be a little bit careful. Like if you have the logarithm, that's not going to be defined for a negative number. So like I said, a polynomial is continuous on the entire real line. So its domain is the entire set of real numbers. So it's continuous on its domain. Trigonometric functions, so this is sines, cosines, tangents, things like that. You have to be a little bit careful because sometimes you end up dividing by 0, for instance, with a tangent. But if you're not dividing by 0, it's going to be continuous. Rational functions, so that was things like f over g. Inverse trigonometric functions, so this is, if I say the sine of an angle is a certain value, I can do something called the arcsine of that value is going to give me that angle up to some sort of multiplicity. And so it's going to be continuous on the right domain and range. The square root or cube root, something like that. Exponential functions. And logarithmic functions. So you can see from this set of sort of 7 things, there's probably not very much that you would normally be able to write down that's not going to be continuous, at least on some domain. And then also, if you have a function of a function, so if g is a continuous function, if g is continuous at a, and there's going to be a value g of a, if f is continuous at that value g of a, then f, so this means composed with, and probably the easier way to think about it is just f of g of x. That's also going to be a continuous at the point A. And so just a quick example. Where is the following function continuous? So it's log of x plus arctangent of x divided by x squared minus 1. So this is a bit confusing sometimes, because if I put a 2 there, generally I mean tangent squared. If I put a negative 1 there, I don't mean 1 over tangent. I mean arctangent usually. So I would say best to avoid this notation. Use arctangent, and if you need that to be a power, just write it as 1 over tangent squared or something like that. So this second bullet point is just a little diversion to explain this tangent, which I think basically was invented because it fit nicely on calculator keys. So I'm first going to look at the numerator here. So I have log of x. That's going to be continuous on its domain, because log is a logarithmic function, and its domain is x greater than 0. And arctan of x is going to be continuous for any x in the real numbers. So the numerator is going to be continuous for any x in the interval 0 to infinity. Now I'm going to look at the denominator. Oops. So x squared minus 1, well, this is a polynomial. We said polynomials were going to be continuous on all of the real numbers, so this is continuous everywhere. And so f of x is then going to be continuous everywhere except where the bottom is equal to 0. So that was my one condition for a rational function to be continuous. So x squared minus 1 is going to be equal to 0 only when x is equal to 1. And 1 or negative 1, except that we're really only considering 0 to infinity because of the numerator. So the only point where I'm going to have a problem is x equal to 1. And so that tells me that f of x is going to be continuous on the intervals 0, 1, and 1, infinity. And by using the parentheses here, I mean 0, 1, so every number that's greater than 0 and less than 1, but not 0 or 1 itself. If I want to include the endpoints in my interval, then I use square brackets. And so basically, it's continuous on this interval except when x is exactly equal to 1. And then just one last thing that I want to stick somewhere in the course, and this is where I think it fits best, is the idea of a horizontal asymptote. And so basically what I'm plotting here is this rational function x squared minus 1 divided by x squared plus 1, and I want to know what happens to that as x becomes large. And if you think about it, when x is small, sort of minus 1 divided by 1 is going to be the dominant part of this. But when x is big, like if x were 1,000, it's going to be 1,000,000 minus 1 divided by 1,000,000 plus 1. So it's going to be pretty close to 1. And so the definition of this red line, so if I have, if I look at the limit as x goes to infinity of f of x, if that approaches some finite value, then I'm going to say that this function f of x has a horizontal asymptote at that value. And the way I've written this, or the way I've designed this example, you get the same value if I go to plus infinity or minus infinity. That doesn't necessarily have to be the case. So this L here doesn't necessarily need to be the same as this L here. And so this line is called a horizontal asymptote if the limit as x goes to infinity is equal to L, or if the limit as x goes to minus infinity is equal to a different L.